Hey y'all, we are back with a little vectors on a plane. We're looking at their magnitude. We're going to do some operations with them and find the vector between 2 points. That's C, D, E, and F out of the text. So here we go. First we want to look at vectors on a plane, just generally how to express them. This is my representation of vectors on a plane. Get it? Like snakes on a plane. Only dorkier. Great. So we can represent them sort of in various formats. And one of them is this unit vector form, where you say, I have this many in the I direction, which is the X direction, and this many in the J direction, which is the Y direction. So one way to represent a vector is with this sort of equation format. You could express this vector OP. This vector is from here to here. You could express this like this, like this, 2 units in the I direction, right? Which means 2 units horizontally, and then 5 units in the J direction, so 5 here. And so this is one way, with sort of an equation format, to express this OP, this is always O, vector. Another way to express it is in terms of unit vectors. This is 2, 5 is another way to express it, which means 2 in the, I should probably do it in the appropriate colors, 2 in the horizontal direction. This is the X piece, and that's this part, or 5 in the Y component, which is this part. So this is another way to express it. Another way to think about this is to say I have 2, let's make sure we're the right color, I have 2 of these, and this thing is a unit vector, means it's 1 unit long. And it's only 1 over in the X and none up in the Y. So this piece is one of these, right? And this is saying I have 2 X unit vectors. Oh, and also I have 5 Y unit vectors. This says I don't go up over any, but I go up 1. That's one of these. So this is saying I have 5 of those. Right? So these are 3 different ways to represent it. Great. Right? Unit vectors have a length of 1, regardless of which way they're pointing. So that's a unit vector, and that's a unit vector because their length is 1. Yeah. Okay. Moving on. So we want to be able to add and subtract vectors. We want to be able to do operations with vectors. So if you are running 4 kilometers one way and then turning 90 degrees and running 2 kilometers south, how do you find that resultant distance? Well, one way is you can use some trig and use the inverse, opposite, adjacent, inverse tangent of 2 over 4. You could also kick it old school and go a squared plus b squared equals c squared, hit a little Pythagorean theorem. Cool. And that's what we're going to do with vectors. So if you're looking at the magnitude of a vector, the magnitude just is the length. It doesn't matter which direction it's going, it's just the length. We can also represent it with this absolute value, which means really the magnitude of it. So, I got the half face going on. So if you are looking at the magnitude of, say, this vector, right, from one point to the next, if you know that it goes over 2 and up 3, there's all sorts of crazy formulas like this in the text about the magnitude of a vector, and really it's just how long is it from one point to the next, and you'd say a squared plus b squared equals c squared, right? And so in this case, c is root 13 because I know that c squared is a squared plus b squared. Feel free to speed me up if you need. I know that a is 2, so a squared is going to be 4, and b is 3, so b squared is going to be 9, so that's going to be 13. So c itself is just going to be root 13. and that's the length of this vector, the magnitude, right? So we're measuring how tall are you. Great. Moving on. So unit vectors, we're number one. Unit, get it? Unit vectors are 1 unit long if they're this way or that way. It doesn't really matter as long as they're 1 unit long. So often you'll see questions like this that it's like, find k, given that this thing is a unit vector. Well, here's a way to visualize that. If you know that this is a unit vector, this hypotenuse has to be 1 unit long. This says I went backwards from our initial point, and I have this vector in the x direction, -1/3, and I have some other vector in the y direction, k. And this is their formula working it out. You can look through that. I like to think about it as a squared plus b squared equals c squared, right? I know this is a unit vector, right? A unit vector means that the length here is 1, so this c squared is 1 squared. I know it's 1. I'm going to put that in a second. I know that one of the sides is -1/3 squared, and b squared is the other side, which is k. Right? So that's all well and good. If you clean that up a little bit, let's see, you get 1, you get 1/9, and you get k squared. If you do a little subtraction and clean it up, you end up with k is the square root of 8/9, right? And if you clean that up further, you get k is plus or minus the root of the top, 8. What is that? I don't know. Let's leave it. And the root of the bottom, 3. It's plus or minus because it's just a length, right? It could be going the opposite way, and we wouldn't know, right? So great. There's the value of k, given that k is a unit vector. I'd like you to pause me, which I'm sure you're happy to do, and try this on your own with this one, right? Find k for the vector blah, given that this is a unit vector. Try that and pop me back on when you got it. Go. All right, so there's our solution. If you got it and love it, keep rolling. If you got it and want to see how it's done, or didn't get it and want to see how it's done, here we go. Says it's a unit vector. This is a length of 1, so I know that it's a right triangle. So we can say a squared plus b squared equals c squared, so half squared plus this other side, k squared, should be 1 squared, which is 1. This ends up being 1/4 is k squared. And when you subtract the 1/4 off, you get k squared is 3/4. And you take the square root of the top and bottom, and you get k is plus or minus root 3/2. Sweet. Moving on. All right, so you're tracking your arch enemy. Maybe, I don't know who you identify with more here, but you're tracking your arch enemy, and you see him or her first walk from point O to point C, and so they walk a certain distance over and a certain distance up. And then you take note of where they are, and they walk then again a certain distance over and a certain distance up, and you want to try to figure out how far over and up where they are in total, right? We want to find a unit vector. Let's make that straight. We want to find not a unit vector, just a regular vector from point O to point S, right? Well, you can add them all up. You can do this sort of thing, right? In the text, it looks like this, right? This plus this, it gets really complicated. But really, you're just saying this distance, this vector, this overarching vector, this guy, is really just made up of the y's added up, this plus this, that's this, and the x's added up, this and this, over this. Cool? So that's what all this stuff means. If you have this as your vector A and this as your vector B, if you're going to add the vectors up, you just add up the x components, and you add up, so that's this, you add up the x components here, this piece and this piece, right? And that's how far over you went in total. and you add up the y components, this piece and this piece, and that's how far up you went, right? And then you ignore all the other stuff and you just figure out this vector based on this and this, yeah? So that's all this mess means. Add up the respective components. So this is your x for your new vector, and this is, when you add these pieces up, that becomes your y for your new vector. Cool? You can make negative vectors. This is my negative vector. He's kind of mad about something, maybe being in math class. And so if you have a, this is your vector, the negative a, or the opposite, will be the opposite of each one. So if here's graphically, here's a, go over 2 and up 3. The opposite of a, negative a, means go backwards 2 and down 3. Straightforward. Cool. Moving on. We want to also, instead of add, we also want to be able to subtract vectors, take a bite out of them. When we added vectors, we looked at, you just added the like x's and the y's. And so you said you went from here to here, and this is graphically how you would represent that. You can graphically represent the subtraction in the same sort of way. Here's A, right? We're going from here to here. But if we were adding B, we'd be moving in B's direction a certain distance. Since we're subtracting B, we're doing the same thing. We're going the same distance as B, but in the opposite direction, right? This distance is the same as this, but it's just in the opposite direction, right? Like that, right? From where the point where A ends off. So this is A minus B, and this is A plus B. Cool? But it's basically the same thing. You take your x components, subtract them, you take your y components, subtract them, and there it is. Cool? That's all that this says, right? If you want to subtract a and b, you subtract the x's and the y's, right? Here's the x's. All right, sorry, there's the y's, there's the x's. Cool? And this is how to visualize it if you're into that stuff. Instead of going up with B, you go back. All right, you try it. Here's A, here's B, find A plus B. Here's P, here's Q, here's R. Find P minus Q, find P minus Q minus R. Try it out, pause me, and I'll show you some answers. Go. Alrighty.